Okay, DMA. We named this not DMA, but eDMA for the enhanced DMA. DMA is very cool. Let me give you an example of when you would use DMA, which is probably the classic one. You know, you're doing serial communication, and so you're getting all these bytes in, and you could have just a buffer, a byte buffer there built into the hardware, custom for that serial peripheral, okay? And we've done this. We do this with some of our other chips. So now maybe you've got 10 bytes that you can store, and then when you get 10, you can interrupt the CPU. I got my 10 bytes, come and get it. And it's a fixed buffer, and it's easy to use, and works fine. But what if you want 11 bytes? Oh, darn. Then you got to do the 10, interrupt, and then do another one after that. So buffers are convenient, but they're not flexible in terms of being, for variable sizes. So at a simple level, DMA can be used to receive, in some cases, serial data or analog conversion data and store it off, because when a flag asserts for that peripheral, instead of selecting an interrupt request, we select a DMA request, and we just copy it somewhere. And we can copy it into a RAM area buffer. And so we can build it, and then after so many copies, then we interrupt the CPU. So it's a flexible size buffer. But the real neat thing about a DMA is sometimes a peripheral just can't do it as we've designed it. And so now you can use a peripheral flag asserting to do a DMA transfer to reconfigure that peripheral, or start another peripheral, or modify another peripheral. And furthermore, using a DMA feature of chaining or channel link, we can now do a transfer from A to B, and then C to D, and E to F. So you could program 10 different peripherals when some peripheral flag occurs without ever bothering the CPU. So you can kind of super glue these peripherals together to have them reconfigure each other when one peripheral flag sets. So you can be very creative with it. So the challenge in the DMA is it's not that hard, but there's a lot of fields to describe what this transfer from A to B. So we have to configure what these transfers are going to be. And we have 16 channels, so we can have 16 pre-programmed transfers when a peripheral flag asserts. And we have to also assign a peripheral flag to these channels. So these 16 channels will have like a multiplexed input. Okay, channel 0, what do you want to connect it to? Oh, I'll connect that to the PIT. Channel 1, what do you connect to? Here, I'll connect that to the EMIOS. We have to connect them to something. And then after we connect them, we have to say, okay, when that flag is enabled and occurs, it goes from A to B, and describe what A and B is. Where is it? How much? That kind of stuff. And we're going to look at that. Okay, so I kind of talked about it's an alternative to a CPU interrupt. And we can use channel linking or scatter gather to have multiple peripherals, for example, to be reconfigured to what I call a super peripheral. But first, we've got 16 channels that you'll see on the right here, and these channels are going to need to be multiplexed to various sources. And some can be always triggered. I'll talk about that in a minute. But the sources, what are the options? We can connect them to SPIs, to EMIOS, not all of them, but some of the EMIOS channels, to the A to D converters, also to I2C for serial transmission. And then some can be always enabled. And why would you do always enabled? Well, one good thing is maybe you want to connect it to the PIT. So maybe you want over the SPI every 10 milliseconds when a PIT expires, write to the SPI to transmit something. So you can do that without an interrupt service routine. You basically, instead of having your 10 millisecond task do something, and maybe there's nothing wrong with that, but you could have the PIT do a transfer to write, maybe read A to D signal, and then take that A to D and send it out to the SPI port. And then also always enabled, maybe you want to just do a block move. This is more applicable to graphics when we get into our Spectrum, some of our other controllers. So this is, first thing we do is we connect a channel to a device. There's a source. You have to enable it. And then you have to say, do I want it always connected, my normal mode, or do I only want to have a DMA transfer when that peripheral says, hey, my flag is asserted and the PIT expires? So this just explains a little more graphically here. When I use the PIT for a trigger, I require the peripheral flag to be, having a request and the PIT. Otherwise, I don't get a transfer. But this is the descriptor. This is what I need to set up. So you can kind of figure out if I'm transferring from A to B. I'm transferring from a source to a destination. So some of these are easy to figure out. Okay, I've got an address of the source. This could be a peripheral data register, or it could be a piece in RAM. Destination, okay, that's easy to figure out. But let's go through them. So first of all, every time there's a DMA request from a peripheral, I'm going to have a transfer of so many bytes. Then I'm going to wait for the next DMA request. Then I'm going to have a loop. Basically, I read here and I write, and I read and I write, read and I write. Maybe I'm just going to read and write once. Actually, with this device, you're probably only going to read and write once anyway, because we're not doing a network hub or a big graphic application. But that's the minor loop. It's typically a loop of reading and writing, and the loop might just be one read and one write. So every DMA request, you execute what we call a minor loop, and you do that for n DMA requests, or n minor loops. And we call that an iteration of minor loops, and so there's an iteration count. We start with a current iteration count, and that count goes down. We also have a beginning iteration count that has to be programmed initially to the same value. So here I get 3 DMA requests and I stop. I'm done. Or I could start over. It depends how I configure it, but typically I'll stop. Now, terms. So address, source, and destination, that's easy. But then there's a size. How big is the size of the transfer? Do I want to read a byte, or do I want to read 2 bytes, or do I want to read a word? And then there's an offset. After I do a read or a write, do I want to add an offset to that address? In other words, if I'm always reading a register and sending it somewhere, if I'm reading a register, then the offset is 0, because I never increment the address. I just keep going back to the same address, and the offset's 0. But if I'm writing to an array, so I'm writing 2 bytes to an array, so I write to the array address, and then I increment by an offset of 2 bytes. And then I write next time, I always add this offset to the address. That's the offset. And then n bytes is just the size of the minor loop. How many bytes do I want to transfer with the DMA request? So n bytes is just for every DMA request, how many bytes. And then at the end of the last minor loop, I have a last adjustment here where I can add either a positive or negative offset to the address. So I can make a circular buffer that way if I want. I can reset it for the next time. So now we have this modulo feature. Another way to do a circular queue is basically you only allow some of the least significant bits to increment. So in this case, I've got it set up so you see 1, 2, 3, 4, 5, 6, 7. These bits, when I have an offset of 4 bytes, these upper bits never increment, just the 0, 4, 8, C. Instead of going to 8, 0, I wrap around to 7, 0. So the modulo feature, I can specify so many bits to allow to increment, and I can get a circular queue that way. This isn't used very often, but that's how it works. Now, scatter gather, and I'll just tell you what it will do and not so much in the details. Scatter gather means once you get a DMA request, then this descriptor that says what you're transferring from A to B will be overridden by another one from memory, from some address in memory. So next time I can transfer from C to D, or either, if the start bit, either right away, the same DMA request, or the next time. And so the other way I can do it is if I have 16 channels and I'm only using 10 of them, then 6 of them are sitting there. And I can load those channels with my descriptors of what I want to transfer and link to them, either at the end of the minor loop or the major loop for to do a different transfer. Okay, the rest of these are kind of straightforward. There is one thing I want to point out though. After you've done your, let's say, 20 DMA transfers, if that's the number of DMA requests or a major loop, you can enable interrupt requests. Or you can enable it halfway through. So if you want to fill up a buffer halfway, then start processing it while you're filling the other half, then you can do that. So you can ping pong back and forth to half size of a buffer. There's a neat little trick to these. If you want to, power or RISC devices aren't really good at bit twiddling, at setting a bit or clearing a bit. So we have this neat little trick. If you want to set a bit in one of these transfer control descriptors, as we call them, you can write to these little 8-bit registers like set start request. You write number 5 and it will go to channel 5 and set that start bit. Or you want to clear the done bit in channel 6. You write 6 there and it will go to the 6th channel and clear that done bit. So it's a neat little shortcut. Okay. As an example, one thing you can do, you can use DMA. You have an emails channel that is getting a pulse train coming in. You can automatically, every time there's an edge transition, capture when it occurred. So that's what this is describing. Or you can generate custom PWM output by basically taking rising and falling edge pairs and writing them to the eMeos using DMA. When it completes one rising falling edge, it'll program the next one. No CPU involved. It's a smart peripheral. Okay, that wraps up DMA. Any questions? Saturated. Thank you for coming. I hope that helps, gives you a head start. Once again, we did not go over the entire chip. The idea is just to give you some technical, advanced information to help you get started.